Okay, so welcome everyone. So the title of my presentation today is Bayesian non-parametric modeling for DER management. Although I will spend probably the first half of the talk, I will try to explain how power systems are changing and what are the challenges that will bring about. And my other goal of this presentation is possibly to attract some interest from people with expertise in statistical modeling, which is not something that I've been formally trained to, even though I use this in research. So if that talk leads to some future collaboration, that would be great. Okay, so first of all, I have to acknowledge the contribution of my, so I have a list of current, former PhD students and postdocs. So I've been working on grid integration of distributed energy resources basically since I came to Australia back in 2010. And that was about the time where DERs, or distributed energy resources, started to become economically viable, starting with PV, but now we also have rooftop, we have residential batteries, home batteries, and electric vehicles are probably not a big thing yet, but once they become, they will create problems for the network. So that's a very hot topic in the power industry. So as I said, I will start by explaining how the power systems are changing with this increasing penetration of DERs, but also large-scale renewables. And then I will talk a little bit about management and coordination of these distributed energy resources, or DERs, and what are the challenges. And then I'll continue. So second part of the talk will be, I will talk in a little bit more detail about one application of Bayesian non-parametrics for DER management, but I also have some future research plans, which I will also tell you a little bit about. So first of all, background and context. I like to start with this slide from CSIRO. This was from back in 2013, so not long after I came to Australia. They convened a so-called Future Grid Forum where they have participants from different industry sectors, and they came up with a prediction of the future evolution of a power system. They came up with 4 possible scenarios, but it's setting up the 2 of them will become reality. The first one is rise of the prosumer. So this word, if you haven't heard this word before, that means basically a consumer who can also produce power. And that means that residential customers with on-site generation, which typically means rooftop solar, possibly batteries and electric vehicles. So that's the first scenario. And the second one is renewables thrive. So, and we are witnessing probably a combination of both. So under this renewable thrive scenario, they predicted that large-scale renewables, wind and solar power plants, which you probably hear a lot about in the news, are becoming cheaper than conventional fossil fuel generation. So eventually they will replace coal-fired generation and gas generation. So what the 2 scenarios have in common, and this is important in the context of the statistical modeling or data-driven approaches that are becoming prominent, is that they bring about a lot of uncertainty. So in the olden days, power systems were quite predictable, but now they are less and less so. So I will talk a little bit about that later. But first, going back to a little bit of history. So that's from 2015, where the Australian energy market operator predicted the price decline of rooftop PV battery systems. So we got it out, right? We are now 20. So we are New South Wales. We are around here. So these are medium scale, or even small scale, probably a little bit higher. So that will be the payback period of PV battery system. When that drops below 10 years, that becomes a no-brainer. Rooftop solar is already a no-brainer. If you have an empty rooftop without PV on it, you should think about whether that's the right thing to do. But batteries are currently still a little bit too expensive, but we are getting very close where they will become price competitive. And that's the driver is, first of all, obviously the technology cost is dropping. So this is from Morgan Stanley research from 2016. So the numbers are not so important. It's just the story behind it. So here on the left, we have how the technology cost is dropping and which technologies split between different components of PV systems. But more importantly, on the right, we have, so this bar on the left is a cost per kilowatt hour used. And we have this range between roughly 50 cents per kilowatt hour and 100 cents per kilowatt hour. But what is more important is when we get additional services that these devices can offer, and they can participate in virtual power plants, they can offer services for network support. When this stack becomes higher, so when this stack becomes higher than the stack on the left, and that basically means that because of these additional revenue streams, battery storage systems become more profitable. So as a result of that, so dropping technology cost, emergence of new revenue streams, AEMO predict that the installation of rooftop PVs and batteries will continue into the future. So let's go to this slide first. And this will eventually lead to a situation where in 2040, again, Morgan Stanley, sorry, Bloomberg predicted that in Australia, we will see 45% of power produced behind the meter. So that means that produced by rooftop solar, other small scale generation, located either in residential homes or small commercial. And that essentially means that we are flipping the paradigm of power system operation on its head. Instead of generation following supply, so large scale generation feeding loads at the bottom, now we are generating increasingly huge amounts of power also behind the meter. And if we, along with that, the utilities are investing huge amounts of money in digitalization. So here we can see that that's global investment in digital electricity infrastructure globally in 2016 compared with some other sectors. So for example, this is, I don't know, video game industry and so on. But it just goes to show that utilities are investing a lot of money in digitalization. And what it means is that all those distributed energy resources, so again, rooftop solar, batteries, electric vehicles, flexible and shiftable loads, and so on, can become active players in power system operation. So, so we have at the same time this emergence of artificial intelligence, blockchain technologies that allow distributed energy marketplaces, ubiquitous connectivity, and so on. So all of that leads to a future where the demand side, which is here at the bottom, becomes a prominent player in power system operation. So we have to contrast that with the situation like even today or maybe in the past. As I said before, we have this bulk generation located or connected to the transmission system far away from load centers, and that generation feeds down power to the customers connected at lower voltage level. So here we have residential. So this figure on the right is just like a schematic representation of the left. So this here is the transmission networks, and the power flow is from the transmission level down to distribution level and to the end load. Now with the emergence of distributed energy resources, so note here that each house has now a PV and a battery. Now the power flows become increasingly two-way. So you can see that those arrows now become two-way. So now in the future, the power can also flow upstream. But now there's an issue with that because traditionally low voltage networks were completely passive. And that will also be important then when I discuss the need for Bayesian nonparametric approaches, because passive, what it means is that power system operators don't really have an idea what happens below the distribution transformer. So everything that is electrically downstream, they have pretty much no observability. And the byproduct of that is that low voltage networks were designed to be completely passive. So there is no active management of low voltage networks. And that becomes an issue when you increase the penetration of rooftop solar in particular, or DERs in general. So when you connect more and more rooftop solar, and this is already happening in many parts of the network. So you can see that those black dots are popping up all over the place. And the red color, the deeper it gets, the more voltage problems you have. So this is obviously just a graphical representation, but it goes to show that as you increase the penetration of rooftop solar without any active management, you create network problems, in particular voltage problems. In the middle of the day when people are not at home, but PV generation is generating power and feeding into the grid, voltages tend to go high, and that creates problems for the network. And we've even come to a point where network service providers, so the operators of low voltage networks, have now proposed to impose a solar export tariff, which means that they will charge customers for exporting power to the grid. And that's obviously not socially optimal. So I will mention later on a possible solution to that, how to do this in a more socially optimal way. Okay, so now I'll discuss a little bit about possible ways of coordination of distributed energy resources. And we came up with this schematic presentation of different approaches. I won't discuss them in detail, but just I will mention them here so that you are aware of the big picture. So when you aggregate distributed energy resources, you can do that along a system scale. So they can be totally system oriented. So just look at the benefit of the system, or completely customer oriented. So they only cater for the benefit of the DR owners. And there is another axis, which is network awareness. So you can coordinate DR so that they are aware of their impact of the network, or they can be completely network oblivious. So you create problems that I mentioned before. So the first one is home energy management, which is obviously completely network oblivious and only focuses on the customer. So that's obviously can create problems as the penetration increases. Now you can do that with operating envelopes, where you impose a limit on the amount of power customers can export to the grid. Then you have peer-to-peer trading, which I won't discuss into detail, but just do you know that it exists. And then we have virtual power plants. And there are several flavors of virtual power plants. The ones that we have at the moment are completely network oblivious and system oriented. So they focus on the benefit of the system. I'll talk about that in a little bit more detail later. And then we also have a network aware version where network constraints are taken into account. So at the bottom, I mean, you can think of that as a fundamental building block. So is a so-called home energy management system. And the idea is that when you buy a PV system and you also have a battery and possibly an electric vehicle and maybe some flexible loads, you want to optimize the operation. So you want to charge and discharge the battery so as to minimize cost. That's called home energy management system. It can be formulated as an optimization problem where you have a sequential decision-making problem under uncertainty. I won't really go into details about that. And today, solutions exist. You can embed that optimization algorithm with different levels of approximation on a single board computer. So Reposit is one example, and SwitchDIN is another example of devices that exist commercially. But they are completely customer focused. So they don't really take into account what happens to the network. Now, when you want to aggregate DERs with other objectives, not just customer objectives in mind. So if you want to take into account system objectives as well, you have to talk about aggregation, or some people also call this orchestration. And in that context, it's important to understand the current, the existing regulatory environment in Australia. So when you buy power from the grid, you buy it from a retailer, but the power is supplied by a distributor or distribution network service provider. So that's the term we use in Australia. And they are separate entities. And that creates some issues which I will touch upon later. So in this figure, we can see that we have a low voltage network. So we have only one physical network. So this is the solid line served by the distributor or distribution network providers. But in principle, you can buy power from different retailers. You can change your mind to go from AGL to Energy Australia, Origin, whatever. So in principle, you can have many. And so what does that mean in the context of market structure? So in the olden days, the power flow was from generators to the transmission system operator, customers, and financial flows were through retailers to the market operator and eventually to the generators. But now with the emergence of prosumers, so that electricity flow, physical flow is still the same. So the physics didn't change. But on top of that, we have aggregators. So these are the emerging entities that can procure services from prosumers. So for example, they can procure services for network support, frequency support, voltage support, or even DR aggregation for participation in the wholesale market virtual power plants. They offer those services to the rest of the grid, but we also have a retailer. So those could be in principle one company, but aggregators might be a separate company. So this is still emerging. But importantly, there needs to be coordination between the distribution system operator and the retailers because of the impact on the network, which I mentioned before. So DR aggregation, you can pose it as in a canonical way as an optimization problem where you minimize some cost function, typically cost minimization. And the decision variables are the decision variables of the aggregator, user agents or prosumers, as well as the network. So just one example I will mention, network-aware virtual power plants. So here the problem is formulated as a multi-period optimal power flow problem. So the optimal power flow problem is mathematically the same as the optimization problem used to dispatch generators in the wholesale electricity market. So it's conceptually the same. Typically, you are minimizing cost. But now the difference between the wholesale electricity market and DR aggregation is that decision variables or the devices that you can use to minimize cost are now prosumer owned, like batteries and possibly other flexible devices. Now, what makes this model or problem complicated are the non-convex network constraints. So here you have a power balance, active and reactive power balance constraint at each node. So this is just stems from the Kirchhoff's laws, and you can see that they are highly non-convex, which makes this problem challenging to solve. Now, the way you can solve it, you can cast this problem as a it can be solved in a distributed fashion, in a rolling horizon fashion, like a model predictive control. Now, if you use short enough time step, like 5 minutes, it can be deterministic because it's 5 minutes is you constantly re-optimize every 5 minutes, so all the uncertainties can be catered by that. So now that's how you would, in principle, solve the aggregation of DERs. And this is actually, actually, I just first explain how you actually solve it in practice. You can decompose this problem if you duplicate the power flows between the network and the prosumers, and this can then be solved using methods like alternating direction method of multipliers. So you can decompose the problem so that each prosumer solves its own sub-problem, which is the home energy management problem, and then you have also the orchestrator or the network coordinator that solves the network problem. And this is beneficial because you can preserve prosumer privacy. They solve their own problem, so they don't have to exchange any information apart from projected power exchange with the coordinator. And now we actually trialed that in an ARENA-funded project consort. So we actually trialed that solution on a small island just off the mainland, just off Tasmania. It's called Bruny Island, where we used batteries and PV systems located in people's homes to solve a network congestion problem. So this project was a partnership between 3 universities, ANU, Sydney, and University of Tasmania, Reposit Power, which I mentioned before, and TAS Networks, funded by ARENA. Now, we demonstrated that this can be done, but in practice, that requires a lot of additional infrastructure on the part of distribution system operators or network service providers. So this is possibly still not applicable in practice. So one issue that actually I'm getting ahead of myself. So the reality today is actually a much more simplistic. So what we do have today, like in commercial operation, are so-called retailer virtual power plants. So that's one possible way how to aggregate distributed energy resources. But unlike that principled optimization approach where you optimize some global objective, social welfare, minimize cost, whatever, here batteries are used, are controlled directly by the retailer. So they use direct load control, and they are used to mitigate price exposure. Right? So retailers, the way it works, they buy electricity in the wholesale market on behalf of end users. And because the electricity price in Australia is quite volatile, it can spike, the price can spike up to $14,000 per megawatt hour, even though on average it's about 50. And that's an issue. So retailers use virtual power plants to mitigate the financial exposure in the wholesale market, and they do so by using prosumer-owned batteries. So the idea here is that they reduce the price exposure, which eventually reduces their cost, and they share part of that benefit with the prosumers, so everybody's better off. The problem with that approach is that it's not really optimal. I mean, doesn't really harness the full benefit of what batteries can offer. But also it can create problems in low voltage networks. So now at the moment, the penetration of batteries is not big enough to really for that to really be an issue. But in the future, that can happen. So that's the state of the art. Now, what are the challenges? So as I said, on one hand, we have this principled network-aware virtual power plant approach that takes care of both the voltage problems and congestion problem in the network. This is explicit in the formulation of the optimization problem. But unfortunately, the industry is not quite ready yet. The additional infrastructure that needs to be put in place to make this happen is still far away into the future. So the reality today is that there is still limited observability of low voltage networks. So from that perspective, not much has changed from the past. So low voltage networks are still largely unobservable to distribution network operators. Now, admittedly, there is a continuing rollout of smart meters. Now in Victoria, that was mandated. So now all the customers have smart meters, but other parts of the country, the rollout is still very limited. So what it means is that network service providers have very limited observability what is happening in low voltage networks. And that pretty much makes the approaches I mentioned before, the principal approaches infeasible in practice. And on the other hand, the issue is that regulatory separation between retail and network service provision, which I mentioned before. So then the power is physically supplied to customers by network service providers, but customers have a contractual relationship with the retailer, and they are two separate entities. They don't really talk to each other. So what it means is that even though you do have a smart meter, the distribution network service provider doesn't necessarily have access to that data. They can get it with a time delay, but not in real time. So that's an issue. So limited observability of low voltage networks. So what I also mentioned is that this increasing penetration of DERs leads to a voltage problem. So we have to find a way to deal with that in scarcity of smart meter data and overall limited observability of low voltage networks. So now this leads me to the second part of the talk, which will be of interest for those of you who are more statistically minded. And I will discuss one application of Bayesian nonparametrics for DR management. So I mentioned before that one of the issues with the increasing penetration of both utility scale renewables, so large scale wind farms and solar farms, as well as distributed energy resources, is the increasing stochasticity. In the past, even though the demand was still stochastic, I mean, you can flick your switch however you want. The system operator doesn't have any control of that. But overall, stochasticity was still quite limited. Now, this is changing dramatically. And the main sources of uncertainty are, so I'm talking now about in the context of distributed energy resources, is solar generation. So that's obviously stochastic because of uncertain solar irradiance. The demand is also non-deterministic, so it's stochastic as it was before. But on top of that, we, as a result of people using home energy management system, that demand can become even more stochastic. And then we have electricity prices are also stochastic, but in the context of prosumers, they are typically on fixed tariffs, so that might not be that big of an issue. So now, a possible way of dealing with that stochasticity is to use parametric approaches, use some sort of parametrization, but that parametric models make assumptions about inputs which might change in real time. And the second issue, which I mentioned before, is that the data we are dealing with is sparse. So if you want to fit a parametric model to sparse data, you'll get problems. So the main motivation for using Bayesian non-parametric approaches is this issue of data scarcity, which I mentioned before. So incomplete smart meter rollout. Distribution network service providers don't necessarily know what is happening with customer demand. Even if they do access to data, they lack the infrastructure to process the data. Because in the past, that was simply not needed. the demand side was completely passive, and this is now changing. And it will probably take 10, even more years for that for that to evolve to a stage where that won't be an issue anymore. I mentioned privacy concerns before, so customers might not be willing to reveal private information. Regulatory separation between retail and network service provision. So retailers might have access to smart meter data, but they don't share it with NSPs. And on top of that, they might not be willing to distribute it because there is commercial value in the data. So in this atmosphere of data scarcity, using non-parametric approaches is obviously beneficial. And just to illustrate why we have to take into account stochasticity, we have here aggregated customer demand at a zone substation with different realizations of rooftop solar generation. So this here is the total demand, and depending on how much rooftop solar you have, you can get very different net demand profiles. And obviously, you need a principal way to deal with that. So that's so in this environment of data scarcity, we've decided to use Bayesian non-parametrics, which provides a principled way of handling model uncertainty. So when you have scarce data, you want the model to grow when you get when you observe new data. So in particular, we use non-parametric Bayesian techniques that can extrapolate outside the training or empirical data on which the model is estimated. And it also gives you the inherent variance in estimation derived from sparse data, and it's adaptive to new data as it is observed. So in particular, what we did, we created a framework for synthesizing residential solar generation and demand models, and that was used for impact assessment of PV penetration. So if you want to do a probabilistic analysis of large penetration of rooftop solar, we needed a statistical model of both demand and generation that can be used in Monte Carlo analysis. What we did, we did have access to a limited amount of smart meter data, which we then used to train this Bayesian non-parametric model. So we approached this in 3 steps. So first we clustered observed demand and generation traces based on some feature. Then we constructed Dirichlet distributions over classes using observed frequencies from the previous set. And then we built Markov chain models using traces for each class. And this then allowed us to sample new traces from the corresponding Markov chain model. So the features that I mentioned before are PV system size, number of occupants, typical demand profiles. So you can cluster demands into typical profiles. So for example, a more prominent morning and evening peak, or more prominent midday peak, and so on. So for clustering, you could use k-means, but instead we used this MapDP, or maximum a posteriori Dirichlet process mixture clustering, where the number of clusters is not needed in advance. So there's no assumption about the number of clusters, which is obviously beneficial when you have scarce data that you don't even don't really have any intuitive knowledge about. So then after this clustering, clusters are defined by centroids and variance, so they can be sampled using a Gaussian mixture model. So as an example, here we have an example of modeling categorical data. The categorical data was PV installation size. Note here that the numbers are, so this is kilowatt hour, so that's energy generating in 1 hour. So if you just take that away, you get installed capacity in in kilowatts. Actually, it was in 30 minutes. So you have to multiply that by 2 to get the PV size. You can notice here that the PV sizes are quite small. So that would be 1 kilowatt, 3 kilowatts, 5 kilowatts. That was almost 10 years ago. So PV sizes were much smaller than today. So if you are wondering about the numbers. So as you can see, we clustered PV sizes, and we came up with 3 clusters. And you can use that Gaussian mixture model to sample from that. And you can do the same with other categorical, other features of profiles. So then once we have a vector of cluster counts, we use that as a hyperparameter alpha of a Dirichlet distribution, which was itself sampled to yield a categorical distribution over the features. So the benefit of the beauty of this approach is that the Dirichlet distribution retains the variance in the estimated distribution of features, which reflects the paucity of prior data available, which is ignored by frequentist approaches. And so finally, we created a conditional Markov chain model. So for example, this here shows you a matrix of the evolution of the demand, which you can see that, so that's the state in one time slot, that the state in the other time slot. You can see that if the demand was low in a particular state, it's likely to be low also in the next time step, and actually the red is high. So you get the idea. So you basically you create this Markov chain that then allows you to create synthetic data profiles. So here are the results. So here we have a plot of, I don't know how many synthetic demand profiles. And if you lump them together, you can see that they closely match the observed profile. So the red is the aggregated, I think we use 130, and we synthesize like 1,000 demand profiles, and you can see that the aggregated profile, they match quite well. And on the right, just another demonstration why we need to use statistical approaches. If you simply use averages, so even for a 100 penetration of rooftop solar, so if every house has a rooftop solar, if you take the average, you will still get you still won't get reverse power flow. Whereas if you use a statistical approach, you can see that in some realizations, the total power flow can actually be negative, which means that that particular customer is feeding power into the grid. And this is obviously missed if you simply use averages. So finally, just a demonstration how that was used in practice. So we use that to do a probabilistic impact assessment of high penetration of rooftop solar in distribution networks. So this here is a single line diagram of a typical distribution networks. So these distances are a bit funny numbers. So this is roughly 200 meters, and this is also like roughly 200 meters. So that would be a residential suburb. So that here is the distribution transformer or green kiosks you can see on the streets. And we have a distribution network with, I don't know, a few hundred customers. So what we did, so we created synthetic demand and PV generation profiles, and then we played with PV penetration, PV sizes, different battery storage, and then we ran a power flow simulation to see what happens under certain penetration of rooftop solar and batteries. and these are the results. So I won't really go into details, but what is important is that probabilistic analysis gives you also uncertain bounds, not just point estimate of I don't know, voltage problems, loading level, and phase unbalance. So these were the performance criteria we focused on, but you also get this probabilistic bound, which is also important. Okay, so that was what we did in the past. Now a couple of current projects that I don't really have any results to show you yet. So the first project is operating envelopes with partial observability. So I mentioned before that when you have a large penetration of rooftop solar, it can happen in the middle of the day that voltages get too high. So this here is 255 volts. So I don't know, the limit is 240 plus 6%, which I think it's 225 volts is the upper limit. In the middle of the day, when people are away, nobody is using power, PV are generating and sending power to the grid, you get over voltages. And that's already an issue in many parts of the network, in particular Queensland and South Australia. So network service providers have come up with a fairly blunt instrument, which is to impose a blanket constraint on PV penetration. So for example, depending on the network, they say you can export maximum 5 kilowatts and that's it. But if your system is 10 kilowatts, you're pretty much wasting half of it. And that's obviously not good. So the motivation for this project is to come up, is to compute operating envelopes that better reflect the reality, but we need to do so in the environment of scarce data. So that I call that partial observability. So the way we are going to approach it, we are going to use Gaussian process regression to forecast PV and demand using limited smart meter data and possibly some metadata as input. So for example, some customers might be on cumulative meters, so we know their energy consumption for every quarter, but that can still be useful to get an overall sense of what is happening in the network. And then the result of those Gaussian process regression are obviously the point estimates and also probability bounds. So you can see that how much that demand can vary in real time when you do this forecast for day in advance, for example. And those probability bounds then serve as an input into the computation of operating envelopes. And that the computation of operating envelopes is formulated as a robust optimal power flow problem to cater for the uncertainty. And once you get those operating envelopes, you send them back to prosumers, and they can then optimize or run their home energy management system against that. Now, the second project, and that's my last slide, is diversity modeling. So I mentioned before virtual power plants. So virtual power plant conceptually is aggregation of large number of distributed energy resources. So they collectively behave as a dispatchable system resource. So that's the name power plant. So they mimic the behavior of conventional dispatchable power plants. So that means that they can play in the energy market, they can bid in the wholesale electricity market, they can offer frequency control services. But the issue is that when you aggregate prosumers or customer-owned distributed energy resources, there is a lot of stochasticity that stems from, as I mentioned before, stochastic PV generation, as well as stochastic customer demand. And that's obviously not good. If you have a VPP owner who wants to play in the wholesale market, but has really no control over the uncertainty bounds, they are really in a bad position to mitigate against that uncertainty. So the idea here is to use, again, Bayesian nonparametric. So in particular, we use Bayesian vector autoregression to simulate behavior and geographic conditional dependency between different prosumers that participate in a VPP. And this allows then modeling the aggregating variance of the VPP output, which then allows the VPP owner to get a better sense of the variability, so they can probably hedge against that risk. Okay, so that's all I had to present today. I will be happy to take questions.